Hey, good morning. So today I'm going to finish up this chapter on CPU scheduling, and this is where we left off last time. We were talking actually about load balancing, and you might need to consider one factor, which is the kind of the closeness of what the process has to the processor, because there are several considerations. One, as mentioned last time, was the cache, right? Because it takes a while for the cache to fill up. And when the cache is filled up, it runs more efficiently, at least probabilistically speaking. There are other considerations too, because especially when you have a memory architecture that is not uniform, or NUMA architecture, then that means there are some memories that are closer to a given processor than to other processors, right? You've seen NUMA organization before. So yes, even though the memory is accessible from other processors, it's slower because it's farther away. And that would be an example of a non-uniform memory architecture. And this, the way this is done, and an example would be the IBM Blade architecture, is so that they want to optimize for when it's placed closer together. And that way it's more efficient than if you want to make it equally fast for everybody, because that is actually a harder problem, especially if you have to travel a longer distance. So when you have this kind of non-uniformity in where the memory is relative to the processor that has to use that memory, then you have the issue of affinity. So affinity is really how, you might say, how good are they as a match, right? They're probably better friends in a way of as one way of viewing this, or they execute more efficiently, they work better together, right? So by they, I mean the processor and the process. So there are certain processors that are a better fit for certain processes than others. And this is not necessarily a static issue. This could be as it's running, because certain processors already has its cache warmed up for a given process. Then it's going to be of higher affinity. So affinity can change over time. Or it could be more of a static feature. That is, well, because it's a non-uniform memory architecture. So when you place the process away from where it needs to access memory, then it makes it less efficient, right? So there's both the static and the dynamic aspect. Okay, so when you do scheduling, oftentimes the API provided by OS allows you to set certain kind of affinity. And these are called soft affinity and hard affinity. But not the OS is not obligated to provide both options. Okay, so soft affinity means the OS is trying to keep the process on the same processor, because not moving is high affinity. But in case of load balancing needs, okay, fine, it moves. But where do you move to? Well, you hope to move to one with better affinity, because that means the cache doesn't have to take longer, or the memory access is not as long. So the load balancing move is the migration is more effective. But the soft affinity actually means, well, but I'm going to consider all possible cases. Okay, so that means even if it is a processor that is far away and when it accesses memory is not so efficient, I would still consider it. So that's called soft affinity. That means the hard and soft means how restricted or how free you want them to choose from. Whereas hard affinity says, well, I know what I'm doing. When you migrate here, this is a subset. You're only allowed to, or you being the OS scheduler when it's doing a process migration, only allowed to move this process to this subset of processors. Okay, that will be hard affinity. It's not allowed to go outside, even if there's another processor farther away that's idle, doing nothing. Right? So you can think of different trade-offs there might be between hard affinity and soft affinity. So load balancing is said to counteract processor affinity. Why? Because if you're running on a processor, not moving is actually a good thing because you don't pay that cost, right? And even if you pay the cost, it still takes time. It's just like if you move to a new city versus staying at home, right? Is it worth it for you to do the move? Because when you move, you have to find a new apartment, have to buy new furniture, maybe have to get to know the environment. Maybe your parking is some farther away. You have to change certain things, and it's not the same as what you're used to. And so there are some dynamic and static aspects. And here they're talking more about the dynamic aspect. So like the cache, and then you build up the cache, but oops, sorry, now you do the migration. Even whether you do hard soft affinity, you still have to start over, rewarm up the cache. So then it starts running more efficiently, right? So anytime you do a move, that in other words, load balancing, then that's actually likely to do bad things to or decrease the affinity that processor has onto its target processor. So NUMA looks like this. You have a computer, multiple, I might say cards of CPU memory, but they have a bus. So because they are in the same computer, there's some ways through some bus or bus hierarchy for one CPU to access memory on a different card that's supposed to belong to a separate CPU, right? And so that way, well, you can imagine if I access the same memory on the same card, it's likely to run fast. If I access memory on another card, I have to go through the bus hierarchy, and perhaps that other CPU on that card has higher priority. Then the access, you can imagine, is likely, if not definitely, slower. But still, is it worth it for you to do a migration to a processor like that? It's kind of like you could live in the city, but it's very expensive. At least you can commute by walking versus you live far away, but then you spend the time on the bus every day with the traffic. But then at least you can afford to live far away, right? That's kind of this cost trade-off. Do you want to do a migration and pay the slow access cost, or do you stay in there, but then you're contending with many other processes on that same processor? So this kind of CPU scheduling plus memory placement is an issue. If you want to optimize this, then it's most likely another NP hard problem. And so again, there are these heuristics to help you do that. But the thing is, you want to have some kind of affinity measure so that you put them in the priority queue. And even if it's not optimal, you go for the target processor that has the highest affinity, or at least higher affinity. Okay, with heterogeneous multiprocessing, well, you have to be careful with that, what the term means, right? We've seen symmetric versus asymmetric, now heterogeneous. Remember, symmetric versus asymmetric refers to who does the scheduling, remember, right? So symmetric means what? That is, every processor gets to run its own scheduler. Asymmetric means there's one processor that does the scheduling for all the other ones. The other ones are kind of slaves. Heterogeneous multiprocessing has nothing to do with that. It actually refers to the different, almost like classes, but more like power versus performance classes of processors that you mix in the multiprocessor. So what would be an example? Example would be a lot of these modern mobile processors on your smartphone, tablet, iPad. So one typical example is the ARM, big little architecture. Funny, they spell big with the lowercase and little with uppercase. That's a gimmick. But anyway, so what is the ARM big little? So instead of just a like Intel style multi-core, which they just duplicate these same core, here they actually have very different designs. Big means one that is optimized for high performance, and little doesn't necessarily mean it's tinier. It's optimized for lower power. Okay, Big doesn't mean the core actually is physically bigger, right? So this really is a power consumption. So little power consumption or big power consumption, and they mix them. And so as you can imagine, they are likely to be done in very different designs, or maybe clocked differently, or maybe powered at different voltage levels, right? So why would you want something like that? Well, guess what? I mean, on a mobile processor, your load can vary a lot. A lot of times in my pocket, not doing very much. So why would I need a big, powerful processor just to be doing idle tasks? That would be much better if I migrate the task to a little processor and you shut down or even power off or put suspend mode on the high performance one, right? So because all it does is periodically check, oh, do I have a network packet, or do I have update the clock, or I mean, it probably doesn't even need to do much refreshing. Maybe some background task, okay. So and then, but you now want to start playing game. Wow, it's very computational intensive, multimedia, and you're running multiple threads at the same time. Then the user expects high performance, right? And they do know that, yes, by playing game, I'm going to shorten my battery by a few hours, but they expect that. So that's reasonable. So in that case, you then, the OS can migrate the tasks from the low power, low performance one to the high power, high performance one. And then that's better user experience, right? And then so it does this kind of migration. And so that will be an example of heterogeneous multiprocessing, okay? So they run the same instruction set architecture, the same binary can run on both classes. And in fact, it doesn't have to be just a single one. You could have multiple big, multiple little ones. And so this is where migration is really driven not so much by the kind of, you might call performance driven. This is actually performance and kind of energy kind of trade-off, right? So overall, you are at a better point both in terms of user experience and in terms of battery life. Okay, so I'm going to switch gear to real-time scheduling, and this is a very different kind of topic. And in fact, there's a whole community of researchers doing nothing but real-time scheduling, and it can be very, very mathematical. However, you can't just do math and prove things, and you got to run it somewhere, and that's where OS people come in. But OS people have their own style of doing things, so this is more of a subset, an intersection between what the OS community does versus what real-time system people do. But real-time scheduling is a lot more than what I'm going to talk about, a lot more than what the book covers. Okay, so there are real-time systems classes you may be able to take on this topic. So real-time versus non-real-time. Well, the key difference, as you can guess, is really timing part. And it's not just like the execution time, like how long does it take? That's like the CPU burst, I/O burst we saw last time. Here, this is more like when you have distance between time. Or latency or duration or deadline, this kind of thing. So it may be relative to the beginning or to the end, okay? Now, and so for a non-real-time system, time is only a soft, it's more qualitative. So certainly if you do it faster, yeah, users may be happier, but if you do it slower, fine, okay. No, as long as the result is correct. But for real-time system, if you don't do it within the timing constraint, then it's considered to be incorrect. It's part of the correctness. But of course, how strict you consider this correctness. That's the difference between soft versus hard real-time. But at least it's making an effort in this case of soft real-time, and it has to make a guarantee in the case of hard real-time. So real-time is not the same as speed. A lot of people think, okay, if I get a processor that's fast enough, it's got to be real-time, right? Well, no. Yes, you have better chance of meeting the real-time constraints, but real-time doesn't always imply fast. Sometimes it actually means you shouldn't be too fast. Just like when you drive on the road, if you drive too fast, you get a ticket. That's that's another constraint. You can have constraint from above and from below. So you may have kind of a minimum or a maximum kind of constraint. So minimum separation. So a lot like when you take medicine. Like doctor says, okay, 3 packs of medicine a day, take with each meal. But what they mean is, well, assuming your breakfast is at some time, and a few hours later that's your lunch, and a few hours later that's your dinner. But if you say, okay, well, today I'm gonna take breakfast at 11 o'clock, lunch at 12, back to back. Well, that's that's not what they mean, right? They actually use breakfast and lunch as a way to suggest that minimum separation. But if you take 2 packs of medicine back to back, you actually run some risk, right? It could be bad for your health. It could be, because the dosage could be too strong. Or, I mean, imagine you haven't taken your medicine for like an entire week and say, oh no, I missed the medicine. Do you take the entire week of medicine and you take it all at once? No, you don't, right? So that is a violation of minimum separation constraint. So that's an example. Too fast, right? Or you take the entire week of medicine all in one shot. Hey, I'm done with the rest of the week. Can I do that? No. Right? So that means that separation does matter. Okay. So doing too fast is not always the same as real time. It does mean timing constraints. And here, they're really just considering deadline for the most part. But strictly speaking, that distance constraint or minimum separation constraint is also there. Okay, now soft real-time versus hard real-time. So really the fundamental difference is whether the system is making its best effort versus making strong guarantees. And how can it say, okay, I'm going to choose making best effort, or can I choose, well, that's dictated by the application. So multimedia applications tend to only require soft real-time in the sense that, well, there's a frame rate to keep up, right? And so even audio has frames. And so when you play like a streaming video, YouTube, then you do need certain rate to keep up with certain rates. But then these have been done so that they adjust the quality of streaming depending on your ability to meet timing constraint or ability to stream data over the network. So if you miss a few frames here and there, you might not even see it because they've done so much in terms of the kind of funny coding, space-time coding, all those coding, so that it kind of interpolates in between. So yeah, you might skip a pixel here and there, but it's going by so fast that you're not going to notice that. So missing once in a while, it's okay. Well, that's called a soft real-time constraint. Now, hard real-time, on the other hand, has to make strong guarantee, not just making a best effort, right? So what would be example? Like your autonomous driving car, your airplane control, your nuclear power plant control, all these mission-critical type of systems. So if you're off, the timing could be off, and then it causes a chain of failures. That's going to be bad. So they would require hard real-time. And that means the system has to make strong guarantees. And so that's really the primary difference. And then the way you schedule these is going to be different. And here's some terms from the book. And you probably should know this, but I think there may be different ways of talking about these terms. But anyway, so event latency is from the time an event occurs to the time the event is serviced. But which part? Is it starting to service or finishing service? Well, this book a lot of times refers to starting to service. Interrupt latency is the amount of time from the arrival of an interrupt to the time that ISR or ISR execution. Again, are you talking about beginning of ISR or end of ISR? Well, in this book, I think a lot of times they don't tell you, but they really mean the beginning. Okay, because once you start running the ISR, okay, you're at least on the right track. Okay, so the book may or may not tell you, but oftentimes they assume it's the start of handling. Okay, and once you start running, the assumption is that, as we saw the last time, the delay or the number of instructions in an ISR is relatively short. So that means it's within some bound. Okay, and interrupt latency in a real-time system should actually be bounded for you to make strong guarantees. It's not just minimized, because minimizing is kind of, okay, I'm trying my best, but what if I couldn't do it? Well, then you couldn't make that guarantee. Now, dispatch latency is the amount of time from dispatcher for the dispatcher to switch a process. That means saving the state for one, picking the next one. Hopefully, the scheduler already puts in some priority queue. So fixed cost, and then restoring the state for the other or starting a new one. And so dispatch latency actually has additional parts. So it has the conflicts phase and dispatch phase. Okay, and then, but anyway, so that these parts, I'll explain conflicts phase. But these two parts add up to the dispatch latency, and this dispatch latency is best minimized if you have a preemptive kernel. So what's the conflicts phase? So, well, there's the preemption, and so that means, well, the kernel itself may be doing some system call, may doing some other service. And so it's not just the user process that get preempted. The kernel may need to preempt whatever it's doing, just so that it can meet real-time latency. But by preemption, as we'll see in the upcoming chapter, you gotta do certain things to ensure you don't get into race condition. And one of those things you do is not just placing a lock. What if somebody's already locking a resource? And that could be a problem, and it would cause what's called priority inversion. And so, because if once you lock it, you kind of become the highest priority, even if you're running as a low priority process. So suddenly, a low priority process can block out somebody else through the mechanism of locking. And we'll talk about locks in the next chapter. And so, to meet real-time constraints, what happens? Then the kernel has to say, well, yeah, sorry, you're a low priority process, so you have to lock. Some other higher priority process is coming in. I'm going to have to steal the lock away from you. So then cough it up. And then, so the lower priority process said, oh, okay, well, it doesn't even get to say that. No, its lock just gets grabbed away. And higher priority process, hey, good, I get to execute. And then that finishes, and then OS sneaks back and locks it for the low priority process. Okay, so that's what an OS, a real-time OS, may have to do if it does preemption. And that is one reason some real-time systems researchers says, preemption? No, don't. That's too scary. How you can even reason about preemption? So there's one class of real-time systems researchers really frown upon preemption because they say, preemption, you're just OS people. You don't know how scary we want to make strong guarantees. Then you're stealing away the locks from processes. How are you going to bound the time, right? It's all implementation driven. Your correctness cannot be proved just mathematically. You have to prove the correctness of the implementation. But how do you prove correctness of implementation? You can't. It's an undecidable problem. So there is a class of real-time researchers that just say, no, I refuse to do any preemption. I'd rather use a much faster processor and do everything non-preemptively. At least I can reason about it, right? And what it executes is within what's decidable because it's just code with bounded delay. I can count instructions. And this is the kind of thing like companies like Boeing, right? And Boeing recently got into trouble with their 780 or 730, well, one of the plane models. But before, Boeing was very conservative. They were using processors from 30, 40 years ago. They were scheduling instructions, machine instructions by hand so that they can calculate the exact latency. That's how strict they wanted it. And for good reason, and Boeing was one of the safest aircraft makers. But now then people demand much more features and much more in terms of utilization, running much more complicated because you can't do this by hand anymore. So, well, yeah, so there's something to be said about these researchers who are adamant about no preemption, because you could get into trouble. And also another thing with Mars Pathfinder, you might know, now NASA sent these little rovers up to Mars, and then solar powered little cars running around and taking pictures and then collecting soil samples. It was a real-time system. And guess what? Because of preemption and also priority inversion due to this improperly handle of the locked resources, got stuck. And couldn't do anything. And so they had to debug remotely, log into a shell on the little rover. And then, of course, in the latency, it's like minutes, right, from Earth to, and then type in VI or a little shell. Not that different from what you have to do with a little ETSIM51 here. And then they found, oh, okay, this is a priority inversion. And then they manually kind of reset that part, and then it started running again. So there are some really, really tricky timing issues here, all due to preemption. Okay. Anyway, we'll get to talk about more of that. But for real-time systems, it's even more of an issue. Okay. Now, so for that reason, scheduling could be done offline or online. And certainly some researchers say you got to do everything offline, or pre-runtime is their term. What does that mean? That means you mathematically prove that these tasks can all meet their hard real-time constraints before you start running, before you power up, or before you say, okay, start executing this real-time segment of code. And so that means your workload has to be known or be bounded before running, and you have to perform some kind of schedulability analysis before running. Now this schedulability analysis could be done by something separate. It could be done in your Python code, MATLAB on an entirely separate computer. It doesn't have to be done on the computer as the OS that's dispatching. So in those cases, if you can do offline scheduling, oftentimes your scheduling is minimal or none at all. All you have is a dispatcher, and it's just following the schedule pre-computed. Okay. Now, online scheduling, as you can imagine, most done by OS people. Hey, we have a multitasking preemptive system. Let's make it real time so we can sell to more customers, right? So, and we don't care if you have you want to do schedulability analysis ahead of time, okay? But we handle online too, and so then online you can keep adding tasks. Hey, do this other task, or you're done. Okay, give you more tasks as it's running. And so that means at runtime, it actually gets additional requests or new tasks coming in. And it has to, and if it's a hard real-time system, then it has to make the guarantee. It has to do the schedulability analysis at runtime, at the time of taking a task request. But guess what? If I just keep giving this real-time, hey, more task, and then at some point it's going to say, no, sorry, I can't take any more, right? So that's called admission control. Admission control is the OS, real-time OS at runtime, getting requests for adding new tasks. And it needs to say, yes, I can take another task and meet everybody's real-time constraint. Or beyond a certain point, it says, sorry, we're full. You can't just keep giving me requests. I'm going to reject because I need to continue meeting the real-time constraints for what I already promised to do. Okay, so that is the proper way for these online schedulers to handle the dynamic nature of these task requests coming in at runtime. Right? So yes, admission control says yes, I admit. So that means accept a new task, and then by the time the condition is, of course, everybody timing constraints can still be met. I made a promise as a hard real-time scheduler, or if it can't meet it, well, the best it can do is keep the promises it's already made, but then say this one, no, I have to reject you. But if that causes bad things to happen, well, sorry, not my problem. You can do task migration. You could do, or ask another process, take different measure. Okay, so it's not ideal, but then that's the fact of life. Okay, now these schedulers, at least for the most part, can be periodic or aperiodic. So in English, the A prefix means the kind of the opposite, right? So not periodic. So periodic means the task is recurring at a regular interval. So there's a rate that's assumed. And as part of taking the request, you actually need to say, okay, don't just tell me how frequently you run this. How long does it take you to run this task? So whoever making the request has to also provide the execution time. And this could be kind of an estimate because, as we saw, CPU bursts can be known for sure. It's an undecidable problem, but then you can at least estimate. And you're usually conservative, so that means you run a loop, run the same code 1,000,000 times, and then you measure the time, and then you see the worst case, how long it takes. And if you're running 1,000,000 times, the worst case is this time units, you maybe add a couple percent or 10%, 20% margin, okay? And then that you use that as your execution time estimate. Deadline, so deadline could be the same as a period. So that means if the period is once a second, it could be the case that deadline is at the end of that period. But it could be stricter. It could be before the end of that period. Okay, but it's relative to each period. There could also be a release time within that. So that means, yes, this is a periodic constraint, but then you can't do it right away. There's a minimum wait necessary, and then anytime after that minimum wait you can do it. So that's called release time. These are possible variables. Aperiodic, on the other hand, the task is either non-recurring or it's recurring but not at a fixed rate. So that means it could happen, but with at least you have to tell the system what's the minimum separation. And so that means you can't have back-to-back of the same task that needs to be scheduled multiple times. It has to at least wait for so long before one can come in. Okay, so these are the typical classes of workload that you expect to see. And not surprisingly, always people like priority-based scheduling. Why? For good reasons. One is there's a nice priority queue data structure. Extract, maintaining login time in practice much closer to a constant time. And you could separate the policy from the mechanism. The same mechanism, you just say, okay, well, I prioritize with a different cost function, but the queue is exactly the same, right? Priority queue the same. So same idea here. So the two most important ones you got to know are rate monotonic scheduling, or RM, and earliest deadline first. So any real-time systems classes will teach you at least these two. These are also the most widely used, most widely supported. And so rate monotonic assumes you have a periodic task. So that means it's recurring at a fixed rate. But deadline is the same as the end of the period. So as soon as a new period starts, you may schedule it. And as long as you finish before the end of the period, it's okay. You consider to have met the deadline. There are some variations, so deadline could be earlier than the end of the period, or it could be later than the end of the period. So, what, really? Well, yes, there's real-time systems literature is all over the place, because by varying just one little variable, you get a totally different problem, and the proof is entirely different. And so that's a good thing for especially people who have to publish a lot, because then I just change one variable, hey, new paper, and so then they can do a lot of math, right? And both assume preemption, so both are preemptive. Difference between rate monotonic and earliest deadline first, one of them is rate monotonic is fixed priority, whereas earlier deadline first is dynamic priority. But it's very different because they're based on different cost functions. Rate monotonic is fixed priority based on the length of the period only. It is not based on the estimated execution time of the task. That's a little counterintuitive, but that's what rate monotonic is. So yes, you can have two tasks, exactly same period. One could take longer, one could take shorter, but they get the same fixed priority. Kind of strange, right? But yes, that's reality here. And for rate monotonic, it doesn't make any difference. In practice, you might say, okay, well, I may want to give a little higher priority to the shorter one, right? And that may be the case. But as far as rate monotonic concerned, only depends on the length of the period, nothing to do with the length of the task, okay? And earliest deadline first is much more general in that it doesn't need to be periodic. It handles aperiodic as well. So if you wanted to give it a periodic task, it's happy to accept it. Give it aperiodic, no problem. Right? It's very general. It's also preempted, but the difference is the priority is dynamic. And what is that priority? It's really the time to the deadline. So if your deadline is coming up very soon, 1 time unit away, you get the highest priority. If your deadline 10 time units away, okay, you can afford to wait. Kind of intuitive, right? But then your time to deadline is a changing thing, right? Because as time goes on, you subtract that time to deadline from everybody who's already accepted. So that's really the how these two work. And so let's, well, rate monotonic is another thing you got to know as a student of NTHU, because anybody knows who this person is? Professor C.L. Liu. He was a member of this department. He was actually former president of this university from the year 1998 to 2002. And I had the pleasure of meeting him in person several times, and he also was part of recruiting me to this university. So he took me to this tourist street where they sold snake meat and all that. I didn't order snake meat, but we ate at a place like that. Kind of interesting, very memorable. Anyway, so C.L. Liu, when he was at MIT, Liu and Leyland, 1973. So this is one of the highest referenced piece of work of all times, rate monotonic scheduling. Okay, and really shorter period, higher priority. That's simple. The assumption is that period is fixed and preempted. The priority depends only on period, not CPU burst. This is in contrast to shortest job first, right? It looks only at the CPU burst or remaining CPU burst. Okay, so you can work this out. Say you have 3 task sets, and what are those tuples? Well, the tuple has the period, comma, execution time. Okay, so the first one is a task, a period of 4, execution time burst of 1. Second task, a period of 5, burst of 2. The third task, a period of 20, burst of 5. Okay, so when they all come in at the same time, who has the highest priority? Well, because they all come in, the period is equal to the deadline, right? So 4, 5, 20, even though they're periods, if they're lined up at the beginning, period equals deadline, so shortest period, highest priority, right? So 4 gets first. Only 1 execution time unit, okay, great, it gets to execute. Then here, what's left? Well, so 5 and 2 now becomes 4. Deadline, you have to subtract 1 from period, right? So 4 and 19. Well, the 5 now becomes 4, has the highest priority, so 2 time units. Then you have a little gap, right? Because the 4 doesn't come back until after the 4, right? And then 5 doesn't come back after the 5. And so that is that little slot where it's, oh, well, nobody else. Okay, I'll run this. You're the only one, the green one. So you get to run for 1 unit, but it has still 4 units of burst left, right? Then for at time 4, well, 4 comes in again. Again, it has the highest priority at this time because 5 hasn't come in. This here, the end of period is 16 away, so that's still, it's got plenty of time. 4 gets to 1 unit, and then 5, 2. Well, then by that time, that's 15, 14, 13, still it has time, so it's still low priority. So its priority is low until it starts to get closer to its deadline, and now it gets promoted to higher priority. Then it comes back, right? So as you can see, this fits. And by the time you hit 20, you still have a few idle slots left. So that's good, okay? So that means everybody can meet their deadline, and you still have some slack. And slack is important. And this is where we're doing a schedulability analysis by rolling out the schedule. And this can be done before runtime. Okay, you just need to know what's my task mix, as long as you know the period and burst. The scheduler only looks at the period, not the burst. But when you do schedulability analysis, you have to look at the burst. Okay. Earliest deadline first, on the other hand, is dynamic priority. So now, this example uses fraction, but okay, fine. So period burst again, task 1, task 2. So, and we treat this as periodic because earliest deadline first doesn't care if it's periodic or not periodic. So just for comparison, let's do this earlier deadline first. And so now shorter one effectively also has an earlier deadline. So 0.9, well, because its deadline is coming up first, it gets to run first. And then the other one, 5, 2.3, then it gets to run a little bit, but it gets preempted. So runs 1.1 by the time 2. Task 1 comes in again, so preempts the T2, and then runs a little bit more until it finishes. And then so it's ping-ponging back and forth. So T2 gets preempted multiple times here. And then by this time, T2 finishes, and you do get a little bit of gap. And before, no, this is when the deadline for T2 is tighter than the deadline for T1. So T2 doesn't get preempted at this time, even though T1 comes in at the time 4. The scheduler says, sorry, T2 has a tighter deadline, let them finish. And then so T1 says, okay, fine. Then it waits a little bit, but it still gets to run. And then time comes here again. So you have 2.3, then the next instance of T2 starts at time 5. So as you can see, that's how this works. So this does rely on preemption to work. So schedulability analysis is key. No matter if you do it at runtime or pre-runtime. Now, one reason people like rate monotonic is it has a very simple schedulability analysis, even though that's a conservative one. And it's also called, it's a sufficient condition. It's not a necessary condition. What does that mean? That means I can come up with a utilization bound. As long as you're below or not exceeding this bound, I guarantee that the tasks are schedulable. When you go above this magic number, it may still be schedulable, but it'll take me a lot longer to figure out. Okay, that means I have to come in and look at many other things, so try to line things up. So this is a sufficient condition. So what is it? So the total utilization on a uniprocessor, as long as it's less than equal to the natural log of 2, then, which is about 69%, then you can sufficiently conclude that that task set is schedulable. You can guarantee. So just under 70%. So if you keep a rate monotonic scheduler busy, just under 70%, you don't even have to do anything. Sure, everybody's schedulable. Like, wow, really? Yes. That's really the contribution of that paper. You should take a look. It's beautiful proof. It's very mathematical, but beautiful results. So that's why a lot of people just love this piece of work. And yeah, in fact, you can push the schedulability with a much higher utilization. So utilization, you remember, is the ratio of the non-idle time to total time, right? And you just add up for all the tasks. And the actual bound may be in the 90% or even higher, but then as long as you keep 60, 70%, yes, you don't even have to do much. So, and as we saw earlier, right, processors aren't usually that busy, and that's a reasonable load, okay? So, and rate monotonic is also called optimal for fixed priority scheduling. That means among any fixed priority algorithms, if they can do it, rate monotonic can do it, okay? Or find a feasible schedule. Now, EDF has a different schedulability condition, which is if the total utilization is less than equal to 100%, then it's schedulable. And so what that means is it can fully utilize a processor, okay? And so that's actually also a very interesting result, because you might think, well, really, I mean, you don't need any gap. Well, it's because of the nature of these constraints. They don't have any kind of minimum separation. So the minimum separation is what kills you. You need to idle. Yes, I want to do, but I can't because I have to idle. So that in case you introduce minimum separation, then your total utilization for schedulability analysis may actually drop lower than 100%. Okay, it's optimal for real-time scheduling, so that means any other algorithm solving the same problem can schedule it, then yes, EDF can schedule it. Okay, so EDF does subsume rate monotonic, but rate monotonic does have its advantages because of that schedulability analysis. Very simple to check. So now the rest is probably a little bit more advanced topic. I'm probably not going to spend too much time on them. So virtualization, so you are starting to see more virtualization for good reasons. So virtualization includes not only like your, VMware, VirtualBox, but also containers like what is it called? The Docker, right, and these containers. They're also considered virtualization. Now, so if you start putting things in these virtualization environments, then your schedule is going to behave in a different way. And even, especially for real-time system, as you can expect, right? Because now it was assuming it has the processor. Now it can no longer assume that because it has to share with other things. So it gets much more tricky. It can undo good scheduling algorithm while running as guest. So I'm not going to cover too much of this. If you're interested, you can read it, and there are more advanced courses that do analysis. So real quick, POSIX, real-time scheduling. So POSIX does support like the spec for real-time, and you can pass flag schedule FIFO, which is first come, first serve. Of course, the assumption is it's not periodic, right? Round robin, similar, except it occurs with for threads with equal priority. And real-time scheduling API, well, I mean, just so I can show you, but this is not a real-time systems course, so I'm not really going to spend much time on it. The important part is really what I talked about earlier. Okay, the rest are OS examples, so real quick. Linux has this thing called CFS, completely fair scheduling. It has basically different scheduling classes. Each has specific priority, and there's detail. I'm not going to talk too much, but In Unix-like environment, there's something called nice, which is a way to adjust your process priority level. You could even do this from your command line. And if you do nice, you lower your priority, so then you give more processing time to other processes. And Linux makes use of that. Also mixing real-time versus non-real-time. Although real-time people say, Linux, real-time? No. So everybody has very different idea about what a real-time system is supposed to be. So anyway, I'm not going to get into that argument. Windows uses priority-based preemptive scheduling. Okay, and Windows for a long time, not real-time. And in fact, President Liu, CEO Liu's wife, also very well-known real-time system researcher. She spent time at Microsoft telling Microsoft, you guys systems, Windows is not real-time. Here's what you do. Spent several years, and well, Windows is still not real-time, but she tried. Okay, so Solaris, priority-based scheduling, 6 classes available. Okay, you can read this for your own interest. Solaris does its own scheduling. So, okay, just you got to know a few terms. So, deterministic modeling, queuing modeling. So, queuing theory is a big one for scheduling tasks on not just real-time system, but in OSs. So, there are advanced classes that talk nothing but queuing theory and simulation implementation. Okay, so really that's all I want to cover for this chapter, and look for, we haven't published have we? Not yet. Okay, so look for another Google Doc for the review questions, and also some programming you can try. Okay, see you next week.